Good evening to all. My name is Vijay Raj. I would like to discuss on UV spectroscopy. Spectroscopy, it is an interaction of electromagnetic radiation with a subject or a matter. It is an atom or a molecule. When we allow electromagnetic radiation to interact with an analyte, there are many probabilities. The analyte may absorb the electromagnetic radiation, it may emit, it may transmit, it may scatter. So according to the probability of the analyte to react on electromagnetic radiation, the characteristics of the analyte is studied. That is known as spectroscopy. So we will discuss on UV spectroscopy. UV spectroscopy is one of a fundamental and very important spectral technique which is used to qualitatively and quantitatively analyze majority of compounds. The other name of UV spectroscopy is electronic spectroscopy. So why it is called as electronic spectroscopy is it involves study of mainly three electrons. So one is n electron, pi electron, sigma electron. N electron is present in heteroatoms like sulfur, oxygen and nitrogen. Pi electron is present in unsaturated groups. It may be conjugated groups. Sigma electrons are present in saturated compounds. So these three electrons are mainly involved in UV spectroscopy. UV spectroscopy is categorized under absorption spectroscopy. Reason is these electrons are going to absorb the electromagnetic radiation, that's the UV rays, and we will be measuring how much amount of the light radiation is absorbed by these electrons. Not all the analytes will absorb UV rays. Those molecules which do possess chromophoric groups are capable of absorbing the UV rays. What are chromophores? Chromophores are covalently unsaturated groups. So these unsaturated groups, whenever it is present in a molecule, it is responsible for UV absorption. We can take an example of carotenoids. Carotenoids are possessing so many conjugated dienes. So that is the reason beta carotenes in beetroots. Beetroots are colored in nature. So the color of the beetroots are because of presence of the carotenoids. The molecular structure of carotenoids do possess conjugated dienes, which are chromophoric groups. There are another aspect called oxochromes. These oxochromes are covalently saturated compounds. They are not directly responsible for UV absorption, but when these oxochromes are present along with a chromophore, it enhances the UV absorption. So oxochromes and chromophores both are responsible for UV absorption. The basic principle of UV absorption is two laws are governing the absorbance. First is Beer's law. What Beer's law says is the amount of light radiation absorbed is directly proportional to concentration of the analyte. That means when the amount of the analyte is increasing, when the amount of the analyte is increasing, the amount of the light absorbed will also increase. Both are directly proportional to each other. That is Beer's law. Lambert's law says when the light is allowed to pass through a medium, that is analyte, when the thickness or path length of the medium is increasing, the amount of the light absorbed will also increase. Path length means that's the distance traveled by the light through the analyte. So when the distance traveled by the electromagnetic radiation through the analyte is increasing, the amount of the light absorbed will also increase. This is Lambert's law. So Beer's law and Lambert's law are two laws which are governing the absorbance. There is another important parameter which we need to know uh, in UV spectroscopy, which is used to do qualitative analysis. That is lambda max. Lambda max is it is absorbance maximum. Lambda max is a wavelength at which the analyte exhibits maximum absorbance. Lambda max is a wavelength at which the analyte exhibits the maximum absorbance. So lambda max is unique for every analyte. Because by using the lambda max, we can do qualitative analysis. So as it is unique for every analyte in a particular solvent, we use lambda max to do qualitative analysis of the analytes. So let us discuss about absorption shift. What are absorption shift? There are four main absorption shift. First is bathochromic shift. So these absorption shift are based upon presence and absence of chromophoric and auxochromic groups. When more and more chromophoric groups are introduced into a molecule, when more and more chromophoric groups are introduced into a molecule, the wavelength of the molecule shift to a longer side. Such a kind of the absorption shift is known as bathochromic shift or otherwise red shift. When we remove the chromophoric groups from a molecule, the absorption of the molecule shifts to the shorter wavelength. This is called as hypsochromic shift. So bathochromic shift and hypsochromic shift is based upon chromophore. When you introduce a chromophoric group, when you keep on adding a chromophoric group, a wavelength of a particular molecule shifts to a longer side, that is bathochromic shift. When you remove a chromophoric group from a molecule, the wavelength or the lambda max of that particular molecule shifts to a shorter wavelength, that is known as the hypsochromic shift. There are other two shifts which are hyperchromic and hypochromic shift. So these two shifts are based upon absorption intensity. So it is because of introduction of auxochrome. So whenever we are introducing auxochromic group, the absorption intensity will increase. So because of the increase of absorption intensity, we do observe hyperchromic shift. Hyperchromic shift is because of increase in the absorption intensity. When we remove the auxochromic group, the absorption intensity will decrease. So that is known as hypochromic shift. So these are four absorption shift which are very important in UV spectroscopy. So we do study energy level diagram in UV spectroscopy. So this energy level diagram explains how the n electron, pi electron and sigma electron, it moves from a bonding orbital to its anti-bonding orbital. Pi and sigma electron do possess anti-bonding orbital, whereas n electron do not have any anti-bonding orbital. So whenever n electron absorbs the energy in terms of UV rays, it will try to move to the anti-bonding orbital of pi and sigma. Whereas pi and sigma, as they are having its own anti-bonding orbital, it goes to its uh, anti-bonding states, which is pi star and sigma star. So in UV spectroscopy, there are four electronic transitions. They are N to pi star, pi to pi star, N to sigma star, sigma to sigma star. So these are the four important electronic transitions which we do study under UV spectroscopy. Thanks for watching. Thank you.